Hi, hello everyone. My name is Wen-tau, research scientist at Bayer Facebook AI Research. Today I'm going to share with you some of our recent experience and work on the topic of conversational question answering. So when hearing about the topic question answering, most people think about the scenario of open domain question answering. So a human user may have questions about different topics, and the system is designed to use some large existing sources of knowledge to answer such questions, ideally with some supporting evidence. So although the problem of question answering can be categorized in different ways, such as by the knowledge source, question type, or the expected answer form, how the answer should be extracted or deducted, the implicit assumption behind it is that it's usually just a singleton setup. So a complete circle is that the user asks a question and the system returns the answer, and that's it. All the follow-up questions are treated as independent, unrelated questions. So in contrast, a multi-turn question answering setting would be like the user is having an like the user is having an information seeking dialogue with the system. For instance, when the user wants to know more about football and asks who founded AFL, the agent may give an answer based on different interpretation of the acronym AFL. However, it knows that this entity linking could be ambiguous and managed to correct it from the user's response. In some cases, it identifies some concepts that it doesn't know, and then can ask the user to fill in the knowledge gap explicitly, such as Pacific Northwest, and carry on the conversation. So the conversational setting provides a more natural form of interaction. The user does not need to form the complete, highly compositional questions, but instead can refine their information need gradually in a session. However, this setting also raises many difficult research challenges. For instance, what would be a good experimentation platform to facilitate such research? How should a model detect different kinds of uncertainty and ambiguity and decide when to pose a clarification question? How can we use interactions to enable lifelong continual learning of the system? So in today's talk, I plan to go over some of our efforts in dealing with those challenges and share the observations and lessons we learned. On the task and dataset creation, I'll briefly talk about SQA and QUAC. Both of them, actually, Mohi is also one of the collaborators for these two projects. After that, I will talk about some work on interactive semantic parsing that aims to enable the system to ask users clarification questions. Okay, so one of the interesting challenges in semantic parsing is to build a system that can answer highly compositional questions, such as what is the power of the superhero who is from the most common world and appeared after 2010. So after all, if a machine can do that, it'll be actually very cool because it basically demonstrates that machine probably understands this question deeply. However, it's actually quite difficult for a user to express their information need in such a long, complicated question. So for example, this, in this project, we basically want to decompose a long question into several consecutive questions, and think that this should be more closer to the real behavior of a user. So in this case, we treat the long question as the intent. And then, as you can see from this slide, the first question only covers some of the intent, and then the following up question, the second and third question, their intent can only be fully understood when you consider the previous answers or questions. So we created this data set by using the tables and and also some of the long questions from the wiki table questions data set, asking characters to decompose the questions into sequences of simple questions and identify the answer in the given table. We evaluate the system performance simply by the answer accuracy. So the average accuracy of all the questions was only 44.7% when we designed the initial model. The whole sequence accuracy, which means that all the questions in a sequence need to be answered correctly, is much lower, which was 12.8%. Due to error propagation, the accuracy of the follow-up question is lower. And several neural-based systems have managed to push the performance, but the general trend remains the same. Not surprisingly, with the help of pre-trained models, the model accuracy has been improved quite significantly. The latest results show almost 75% all question accuracy, and about half of the question sequences can be answered correctly. So sequential question answering is our first attempt for approaching the problem of conversational question answering. One of the issues we found is that because we started from existing long questions and asked workers to break them, sometimes the question sequences are not actually very natural. So our next attempt is QUAC, which was inspired by the reading comprehension task. So similar to the SQA setting, if the interpretation of the follow-up questions depends on previous questions or answers, then a system needs to know the context to be able to answer such questions. So unlike SQA, which uses one character to break a given long question, here we pair two characters, one as student and the other as teacher, to stimulate a QA conversation. We first pick an article from Wikipedia. The student is provided with the article title and first sentence so that they know the topic. The teacher, on the other hand, has access to the whole document and can use that to answer questions by choosing a stem. To encourage a longer conversation, the teacher will also provide some feedback to hint whether there could be more interesting follow-up questions. So this slide shows an example of a QA dialogue. We use a section of a Wikipedia article as the document. The student sees the section title and the first sentence. As you can see from this example, the student may start from some broad questions. Based on the teacher's responses, the student may ask more specific follow-up questions or change to a different topic eventually. Among the questions we collected, half of them are factory questions. 20% of them are unanswerable, and 6% of the questions need to resolve some co-references to the documents, and 40% of them needs to resolve some co-references to previous questions or answers. As the dialogue progresses, we see questions become harder. In addition, there's some natural locality in question sequence, as the answer to the next question is usually close to the current answer in the document. So in addition to the common evaluation metric F1, which measures the total match between the predict and the goal answer space, we also introduced the human equivalence score. The human equivalence score basically judges how the system's performance compares to an average human. The QUAC has been quite popular since it was introduced, and the current state of our systems achieved a pretty high F1 scores, but are still quite behind on the human equivalence measure. Concurrent to QUAC, the COCA dataset is designed for a very similar goal. Other than using spans as answers, the answers to questions in COCA can be free from text. In addition, the evidence in the passages that supports the answer is highlighted by the annotators. So in SQA and QUAC, we simulate possible information-seeking conversations between user and the system, using tables or documents as context. While there are definitely great resources for conducting conversational QA research, the static dataset setting is also somewhat limited. For instance, the interactions are really just one way. So users can ask different questions and the system can only answer them. Next, I'm going to introduce a different line of work that addresses the research challenges when we want the agent to ask some questions as well. So in this part of the talk, we assume that the agent is using a database to answer questions. For example, the user may ask, which AL team won the most games in a season? And the system can find the answer 2001 Seattle Mariners from the database. In the conversational setting, we envision that the system can get help from the user and serve the user better. For instance, the system makes sense that, the system may sense that it's not completely confident on the model's prediction and ask the user some clarification questions, such as what does AL mean here? And the user can provide immediate feedback to help the system to derive the correct semantic parse, and that's the answer in the end. Finally, the system can keep improving itself based on the user feedback, even after being deployed. To iterate, we would like to learn semantic parsers with human users in the loop. We view a semantic parser as an intelligent agent that is introspective of its uncertainties and can prompt for user interaction when it needs. The agent should also be able to continuously accumulate user feedback and improve itself. The user only can answer the clarification question based on their knowledge and preferences and understands the system's behavior and limitation better. So in the following, I plan to cover 2 papers on our research effort in pushing toward this direction, and they both are the joint work with several folks at Ohio State University. The first one is an ELP 2019 paper, where we propose a general framework with the goal of making a given existing semantic parser with a given existing semantic parser an interactive one. The second one is also an ELP paper published last year, where we explored learning methods for improving a deployed interactive semantic parser through interacting with users. So based on the observation that the performance on most semantic parsers is still far from perfect, in this project, we asked whether the imperfect semantic parser can still be helpful to the user in practice, just with a little bit help from the user. So our goal is actually to build a general unified framework, given an existing semantic parser with limited modification or customization. We can wrap it with our framework to make it an interactive system. So we targeted this project in the text-to-SQL scenario. Here is an example showing the potential interaction between the user and the semantic parser or the agent. The user first asks the number of schools or teams that satisfy a certain condition, but somehow this condition is confusing to the agent. The agent then initiates a conversation and asks for clarification. It starts with its initial guess on the condition, framing it as a yes/no question. Given that the user points out the initial guess is incorrect, the agent then reframes the clarification question as a multiple choice question. With the correct input, the agent is able to generate the complete correct semantic parse in the end. Internally, the user feedback is not used for creating the whole semantic parse, but only for correcting the piece that the agent is uncertain about. So to enable the interactive semantic parsing scenario, we are first assume that the base semantic parser generates the semantic parse in steps. For instance, it may decide what the select statement should be as the first step, and then move on to determine the conditions. The whole agent-user interaction is framed in this conceptual diagram. On the left side, we have our interactive agent, and on the right side is the environment, which is essentially the user. The communication interface is the clarification question from the agent and the answer from the user. The first component is in the agent is the world model. This is the internal interpretation of the world, which it maintains the current partial parse as the state, perceives environment signals such as user's input, and performs state transition. The second component is an error detector. It examines the latest action and measures the uncertainty of the particular prediction. When the uncertainty of a prediction is under a threshold, the actuator is triggered to generate a clarification question for soliciting user feedback. And we now apply the framework to Text-to-SQL as a case study. So the user gives an initial question at step 1, asking what is the score of the game on November 12th. The agent receives this question and starts to parse it into a SQL query. At step 2, it generates a partial parse select place. This partial parse is validated by the error detector. If it thinks that the prediction is correct, then the parsing continues. Otherwise, the actuator generates a question to let the user verify this partial parse. Here in our example, the agent asks about the selected column place. At step 5, the user gives an answer. This feedback is interpreted by the agent's world model to update the agent's understanding on the user intent, which basically updates the current parse. And this procedure repeats until the parsing completes. So as we can see, this framework makes few assumptions on the basic semantic parser or the formal language, and has the flexibility to replace or improve each of its components. At the same time, it naturally includes human interactions during the process. This allows the user to join the decision-making process and to intervene when necessary. Two components are crucial in determining whether this framework can work in practice. The first one is whether the agent can detect its incorrect prediction reliably, and the second is whether it generates some clarification questions that can be understood by the user. In our implementation, we tried 2 different designs of the error detector. As mentioned earlier, the error detector estimates how uncertain the model is in a particular prediction. Our first design thus compares the probability of the parser's decision with the threshold. If the probability is lower than the threshold, the decision is deemed uncertain and it will a question. The second design calculates the variance in parser's decision. At the test time, we perturb the base parser's parameters using dropout for several rounds and measure the standard deviation of the parser's probability on making the same decision. If the standard deviation is greater than the threshold, that means that the parser is not so confident about its decision, and the agent should request a human validation. So in our experiments, we didn't find Bayesian dropout performance better, so we used a simpler probability-based method. For the actuator, we use a rule-based question generator. We designed a set of domain general lexicon for commonly used SQL operators and aggregators, like the greater than and the max aggregator. We also designed a set of grammar for deriving questions. You can see that from the example on this slide, here we want to ask about the aggregator max in a select clause. To generate a question, we simply replace the specific aggregator and the column with their descriptions in the template. So in our empirical evaluation, we tested our proposed framework with 2 base semantic parsers, SQLnet and SQLover, using the WikiSQL dataset. We compare our system with an existing baseline code, DialSQL. DialSQL trains a simple dialog system to verify the predictions of a pre-selected black box text-to-SQL system. Although its goal is similar to ours, DialSQL is not a general system that needs to be redesigned whenever the base semantic parser changes. We measure the accuracy of the generated SQL query by comparing the query or the execution results with the ground truth. We also compare the average number of questions of each system. We can see that for both SQLnet and SQLover, our system improves the base parser by 10 to 15% in accuracy. by asking a small number of clarification questions. In exchange of the better performance, the user will need to answer some clarification questions to help the semantic parser. The number of clarification questions that need to be posed and answered depends on how accurate the base semantic parser is, and also on the uncertainty threshold setting. For instance, when using SQL Lava, the performance still improves a lot when the system in average asks one clarification question in every 2 examples. Compared to DialSQL, we achieve better accuracy with only half of the questions that DialSQL needs, although our system is much simpler than DialSQL. It's also important to note that our framework can be easily generalized to more complex SQL queries, such as those in the Spider dataset, but it will incur a much higher engineering cost for DialSQL to adapt to complex SQL. The experiment results on Spider can be found in our paper. Now let me talk about the second paper, which is trying to learn from the user interactions after the system has been deployed. Recall that the interactive semantic parsing setting, the feedback signals are the confirmation or correction of the partial predictions that the model is uncertain about. Essentially, the question we ask here is, how can we leverage these incomplete partial labels to improve the system over time? Learning semantic parsers from user interaction has been explored in the past. However, the setting is usually asking the user to validate whether the semantic parse execution sort, the answer to the question, is correct or not. This may not be practical in our scenario if the end users know the correct answer. They would not need to ask the question in the first place. Knowing the correct answer is especially difficult in information seeking scenarios, such as querying a large database. Very often, the best method is still to have the correct structure query. Our focus is that's different from the previous work in that we directly validate the meaning of a semantic parser's constituents. As we will show later, this allows us to train the semantic parser more effectively. Recall that our system collects user feedback in the form of user-guided or corrected parsing actions, such as predicting the table attribute pair after the parser has generated the keyword where. We call such user-guided actions user demonstrations. The goal of our system is to train the semantic parser to imitate the user demonstrations collected during interactions. We resort to imitation learning and propose the NEIL algorithm. Our algorithm is annotation efficient, which means that the agent will only ask as many clarification questions as it needs so that it won't annoy the user. However, the sparse user demonstrations also brings a challenge. We address this problem by collecting not only user demonstrations, but also agents' confident actions without a user validation as training labels. NEIL essentially is essentially a Dagger-like algorithm, which iteratively aggregate demonstration as new training labels and use them to retrain the parser. Recall that we view semantic parsing as the process of generating the output semantic parse in steps. This can thus be formulated naturally as autoregressive action sampling and execution. The state space is defined by the initial user question plus the partial semantic parses that have been generated. The semantic parsing model is therefore a policy function that we want to learn. So our algorithm is very straightforward. In each iteration, it receives a set of user questions. For each user question, it interactively maps it into a semantic parse and collects demonstrations during interaction. As we elaborated, the demonstrations have included both user demonstrated actions and user confident actions. The aggregated training labels, as well as the original data for training the initial model, are used to retrain the policy for the next iteration. Finally, the base policy on validation is returned. So one important question about the algorithm is that while NEIL is annotation efficient, we result in much worse semantic parsers compared to the fully supervised approach. In this work, we also provided some theoretical analysis. The detail is in the paper, and here I'm gonna to report the main conclusion. Assume PySub is the model learned in the fully supervised setting, and Pi is the model learned in the interactive setting by our algorithm. So essentially, PySub could be treated as the ceiling of the performance. So we show that to reduce the difference in loss between these two policies, there are two key factors. The first one is the correctness of the confidence estimation. This is intuitive because if the examples that the agent is confident about the predictions and those predictions are correct, then such examples can provide the right supervision signals for the model training. The second factor is that the initial model performance should be reasonable so that the interactions can be meaningful. Empirically, we evaluate systems on the WikiSQL dataset and use SQL Lava as the base semantic parser. We explore three parser initialization settings, training the same model, but with different numbers of training examples. During the iterative learning, we use the user questions from the remaining training set and simulate user feedback by comparing the parser's prediction with the ground truth. We first compare each system's annotation efficiency. Annotation efficiency. We evaluate each parser's accuracy when their system has consumed a certain number of annotations in training. We compare the full supervised approach, our system with its skyline variant, which represent an upper bound performance of our system, and the self-training baseline, which does not require human feedback at all, but instead takes its own predictions as training labels. We observed that MISP-NEIL enjoys great annotation efficiency, and it additionally has the advantage of collecting annotations from regular users rather than domain experts. For self-training, the number of annotations is always 0 since it does not require human feedback. However, its performance is much worse. We now compare each system's training effectiveness. We evaluate each parser's accuracy when they are trained with the same number of iterations. The results show that when a semantic parser is moderately initialized with 10% or 5% of the original training data, our system can learn a semantic parser that reaches a comparable performance level as the fully supervised approach. And it is annotation efficient, as we have discussed. Our system also outperforms other systems that learn from human users. To summarize, today I'll briefly talk about the research challenges of multi-turn conversational question answering. In the first part, I shared the experience of building 2 different datasets. As I mentioned earlier, while static datasets help quickly boost system development and enable fast research cycles, they still are fundamentally limited. One of the promising initiatives at FAIR that addresses this issue is to have a human in the loop dynamic data collection process. The dataset can be renewed periodically, and human annotators can probe and attack the model weaknesses constantly. In the second part, I introduce our recent work on interactive semantic parsing. The framework helps make a system useful with the help of end users, even when the system is not perfect. And I also talk about how the model can be improved using the interaction logs. There is obviously still a long way to go to build a natural and accurate conversational question answering system, but hopefully by exploring all these interesting directions, we can make rapid progress in the coming years. And this ends my talk, and thank you very much for your attention.